This is a problem from
here's the
8.1,
solution
number
to,
22, where you're given the
8.2,
integral and you need to match
number
what the figure would
31.
be. Something to keep in mind, as I put a note up here,
So in this case, we
pretty
are
much
asked
looked
to
mostly
find the
at
volume
either half circles or
of y
hemispheres,
equals sine
depending
of
if we were
x, the
finding
first
area or
arch,
volume, and
y
triangles
equals
and
0,
cones, again, depending if we
and
were
to
finding area
rotate it
or volume.
around the x-axis.
Deciding between those shapes, essentially
So
what
always,
we
we would
did
first start out with
when
a
we were
sketch.
finding volume, all of our
Here's
cross sections
sine.
were
We know it's a
circles, so they
period
would
of
all
2
have some
pi.
form of pi
So the
r
first
squared.
arch,
The
which
question
is what we are
is,
asked
what would
to
your
rotate,
relationship look like for the
goes
radius?
from 0
If our
to
cross
pi.
section was an
So just the yellow
isosceles
region
triangle,
right here.
we would use
Here we're
proportions
asked to
to find the
rotate it
radius.
around the line
That
y
would make
equals
your
x.
expression in the integral look
So
like
in this
a
case,
linear
I can see that
expression.
my rotation,
For example, 2x
my
or
axis of
3x,
rotation is in
and then
fact
the
one
whole
of the
thing would
bounds
be
of the region.
squared
So I'm going to
because
get
your
a solid
radius in a
circular cross
triangle
section.
was moving
My cross
proportionally along
sections
a
are
line.
perpendicular
For these ones
to
as
the
well, you could draw the
x-axis,
coordinate plane and probably
so I'm going to
sketch
be
the
using
graph
dx. So I need
that you're
everything
actually
in terms
finding
of
the
x.
volume of to figure
So
out
I'm
the
integrating
answer.
these little
However,
circular
if your
disc,
cross section is a half circle, as
cylinders
in a
that are going to have
hemisphere,
area pi r
then
squared,
when we tried to find the
and the
radius of the
thickness is
cross
dx,
section, what we
and I'm
ended
going
up
from
doing
0
was
to
sketching
pi because I
inside a
want the
right
first arch.
triangle,
So
since the
that's going to be
hypotenuse
0
would
to
always
pi,
be the radius of the
pi
sphere or the
r, and the
hemisphere that
radius
was
in this
given,
case is going
and then
from
we would
the
use the Pythagorean
x-axis
theorem.
to the
So your
curved sine of
expression
x.
for your r
So that's the
squared
distance
in your
of sine
cross
of x.
sections
So
would
r
look
squared
something
would be
like the
sine squared of
Pythagorean
x
theorem.
dx.
This one
At
seems
this
to be sort of a
point, you can
combination.
integrate
We
by
have
parts
here
or using
the
the
2
table.
squared minus
And
something
when we
squared,
integrate
which is
from
looking
0
a
to
bit
pi,
like finding a
pi
side in a right triangle
sine
if you know the
squared
hypotenuse
x dx.
using the Pythagorean theorem.
And again,
But this
either way
part,
is
the
fine.
2
So if you
minus
look on the
y,
table,
is itself
or you
linear.
can do by parts,
This is in fact going to be a
you get that
hemisphere.
the
I can
antiderivative
tell that
here,
it's three-dimensional because I
you
see
still
that
have the
I've got
pi, and it's
an
going to be
area
1/2
here. Here's a pi,
times
something
x
squared,
minus
times
sine of
a thickness,
x
dy.
cosine of x.
So if I've got 3
all
dimensions, my
evaluated
area
between
squared
0 and pi.
times my
So
thickness,
when I
that's going to give me
substitute
a
that
volume.
in,
And then I'm
that's going
going
to be pi
from
over
0
2
to 2.
times pi.
To get the
Sine
visual
of pi is
of what's
0.
going on here
And
with
then when
the
I plug in
cross
0,
section,
everything is 0.
I can see that I
So
have a
that's
half
pi squared
circle.
over 2.
The
And they
radius of my
suggested
half
rounding
circle
to
is
the
2.
nearest hundredths place.
Here's
so
the
that
center,
would be
that means this is 2. The
4.93.
radius here is always 2. So what I'm thinking of is measuring a height, and as I take my cross section, since this is ultimately going to be a hemisphere, they look like these little teeny tiny cylinders, each of them with a radius in here, which I'll call little r. Notice that anytime I go from the center to the edge of the circle, that's the hypotenuse of my original hemisphere, which would stay 2. In this case, you're probably wondering, where did they get this 2 minus y from? That looks a little bit different. It all depends on how you define your y. So in this case, what they did was they measured y as the distance from the top of the sphere. If the distance from the top of the sphere to where my cross section is y, and the entire radius is 2, then this distance right here is my 2 minus y. So if I look at this triangle, where again, this length right here is going to be the radius of my cross section, then I know in any triangle, this height from the bottom would be 2 minus y, and the hypotenuse would always be 2, the radius of the hemisphere. So by Pythagorean theorem, we would get that r squared is going to be 2 squared minus this 2 minus y squared. So that would give me this expression, right? Here's my r squared right here. That matches up with this expression right here in purple. So now I can see I have pi r squared times my thickness dy. So I'm stacking up these circles right here, these little mini cylinders, all the way up and down my hemisphere. So in this case, my final answer would be a hemisphere, half of a sphere. I know it's half because I'm only going from 0 to 2. So that would be 0 to 2. If it were an entire sphere, I would have to go all the way from -2 to 2. I would need the bottom half. So this is going to be a hemisphere of radius 2, and that would be your final answer.